Hello everyone, welcome to today's webinar, Insight Through Integration, the Future of the Vitech Solution. My name is Katie and I'm the Communications Manager here at Vitech, and I will be your host during today's webinar presented by Zane Scott. We are excited to share with you more about Vitech Solutions history, inspiration, and future. Zane is our Vice President of Professional Services and our training organization. For the past 25 years, he has built a skill set which enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies across their organizations. He has also taught systems engineering methodology in the practical process context in a variety of settings. Zane has a BA in economics from Virginia Tech and a JD from the University of Tennessee Law School. He completed his postgraduate work in business administration and educational counseling. Zane is a member of the American Society of Training and Development and the International Association of Hostage Negotiators. Before Zane gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar today, so please send in your questions as soon as you think of them through the question tab on your webinar control panel. Zane will answer as many questions as he can today, but if he does not get to your question, we will reach out to you after the webinar. The webinar is being recorded today, so if you experience connection problems during the live presentation, a recording will be available by request within 24 hours of the live version. The recording will be published to Vitech's webinar archive located on our website. I will send out the link in the chat window. So now I'm going to turn over the presentation to Zane. Welcome and thank you for joining us.
Good afternoon and thanks, Katie. And welcome everybody to our webinar. This afternoon we're going to talk about the future of the Vitech solution, and as you might imagine from our title and our company tagline, which is Insight Through Integration, we have an integrated solution with which we have moved for 20 years now, and that we are going to move forward into the future with some new dimensions. And that's what we want to talk about today. So let's get started and begin with where we're going to go. As I said, we have an integrated solution and we're going to talk about that this afternoon. Our solution has three basic aspects to it that we'll be discussing. So as we look today, we're going to talk about mindset, methods, and tools and how those are integrated together. This basically tracks something that Simon Sinek calls the golden circles. Our mindset is our why, and we're going to talk about that today. Why are we doing the things that we're doing? Why are we doing them in those particular ways? Why are we using the approaches that we use? We'll discuss that as our mindset. And then we'll talk about how we do the things we do. And those are our methods. And finally, we'll talk about our tools, the tools that make up our solution. And the tools are what we use to put our methods into action. So we have a basic schema to track our solution with. And as a systems company, that shouldn't be surprising at all either. So we're going to be discussing, whoops, I'm getting all sorts of little computer helps here. We're going to be discussing this schema. And in our schema, we use our tools to leverage our methods, and we use our methods to implement our mindset. And as I laid out, our tools are the what we use, our methods are the how we use it, and our mindset is why we go about it. So we're going to go inside out. Sinek uses concentric circles with why in the middle and how outside it and what outside that. And we're going to go right to the center to get started. So let's begin with our mindset. You can think of a mindset as a paradigm or our worldview, if you will, the way we look at things, the way we structure our thinking. It contains our assumptions about the world, and it really carries, as I said, why we do the things we do. In our Vitech mindset, there are two aspects. topics, two things that I want to highlight for us today. The first one is that we have a systems mindset. We think of solving problems with respect to systems. So we tend to think of problems and solutions in systems. And secondly, we use models as our way of getting at these systems. We use models to think about existing systems. We think about models. We use models to think about problems, and we use models to think about solutions. So we think in systems and we think in models. We'll tackle the first one, systems, first. And the first question, of course, is, what is a system? Now, for the systems engineers among us, this is not going to be a very difficult thing to tackle. We're all familiar with system definitions. I took apart the INCOSE definition here, and we'll use this as our place to begin, our launching pad, if you will. But in the INCOSE definition, it says a system is a construct or collection of different elements that together produce results that are not obtainable by the elements alone. Now, this INCOSE definition basically tracks most of the other definitions of system that you'll see. And I broke it apart because I wanted to look at the different aspects of that definition. And these are the aspects of almost any systems definition. First, we have two or more parts. In order for it to be a system, in order for us to look at it as a system, we must be able to see it as composed of parts. So it has to be more than a single entity for us to get an idea of it as a system. Secondly, it produces results. Systems do something. Systems perform some sort of a function. That is true no matter whether it's a system that we're looking at and describing or a system that we're designing, a system that we're trying to use to produce some desired result. So the system contains two or more parts, and the system produces results. And then, and this is very important, those results are not obtainable by the parts alone. In other words, the system goes beyond the parts. And not only that, but it goes beyond the sum of the parts, as we'll discuss here in a minute. So let's take a little broader exposition of this. This is a quote, by the way, and we're going to look at the quote, and then I want you to be thinking about what's the profession of the person who would say this. According to the systems view, the essential properties of a system are properties of the whole which none of the parts have. They arise from the interactions and relationships among the parts. These properties are destroyed when the system is dissected, either physically or theoretically, into isolated elements. Although we can discern individual parts in any system, these parts are not isolated, and the nature of the whole is always different from the mere sum of its parts. What do you think the person who said this does in terms of profession? Is this a systems engineer? It could certainly be said by a systems engineer. Is it a scientist? If so, is it a physicist? What exactly is this person? It's very interesting because the answer here is twofold. This is a quote from Fritjof Capra. Capra was a high-energy physicist who, in practicing his profession, began looking at the principles of quantum mechanics. And in those principles, he also saw a commonality with Eastern mysticism. Capra, like numbers of people in the 60s, became very interested in Eastern religions, Eastern spiritualities, and mysticism. And he began to see some overlap between what he was doing in physics and what he was doing as he encountered these Eastern religions. And in 1975, he wrote a book about that overlap called The Tao of Physics. And it's a fascinating book. You can find reviews of it all over the map. It's been reviled, it's been loved on, it's been hated on. But for our purposes, the key thing there was the similarities that he began to see, because he not only saw those similarities, but he began to explore in the world of science and to catch similarities between quantum mechanics and high energy physics and other scientific disciplines, and ultimately followed a path that led him to biology. And for most of the second half of his career, if you will, he's practiced his scientific pursuits in the area of ecobiology. He had a number of very interesting conversations with Werner Heisenberg and Niels Bohr, and found some commonality with them in terms of what they were studying and noticing as principles. And these principles that he began to see as overlap have to do with the nature of systems and the way that things fit. Capra thinks that everything, all of the different branches of science and metaphysics and religion and all things are part of a broader system, and that we describe different aspects of it in different ways, but we're dealing with a unified system. And in fact, his latest book, which he calls a textbook, is called The Systems View of Life, a Unifying Vision. It just came out in the last month or so and is a fascinating work. But what Capra was seeing was this principle of systems. And it's summed up in this quote that I've taken from him that we just read. And I would like to call attention to what I think is a critical sentence in that quote. These essential properties, and I have added back the clues to what he does for a living, because instead of just system as I had it portrayed in the first slide of it, it says the properties of an organism or living system are properties of the whole which none of the parts have. And these essential properties arise from the interaction and relationships. That's the crux of what Capra is seeing as a commonality. And that's a very, very important principle for us as we look at systems, as we look at designing systems, as we look at understanding systems. These become very, very critical. So the critical principle that's driving Capra's work in terms of uniting all of these different disciplines in his view is this principle right here, that the essential properties of a system arise from the interaction and relationships among the parts. Now, another very important thing to the way that we look at things at Vitech and the way that we look at things as systems engineers or systems practitioners is that these properties, these special properties of a system, are destroyed when the system is dissected, either physically or theoretically, into isolated elements. If you pull the system apart, certainly if you pull it apart physically, it can no longer perform its functions. I've been in the car this afternoon driving. That wouldn't work so well if while I'm here in the office giving the webinar, somebody's in the parking lot taking my car apart. It's not going to perform those functions that make it an automobile and a method of transportation when I'm done if it's physically taken apart. Nor would we be able to view it as a system if we dissect it theoretically. And one of the most important things that I want to say this afternoon is that as we do things that fragment our approach to systems, that fragment the systems that we study, that change the way we view things and specialize and narrow our focus, those things tend to destroy the system's view. And while it may be good to understand individual pieces, we should never mistake that for understanding the system itself. You know, we have a temptation as children of the Enlightenment to think that understanding comes from analysis, from breaking things down, from disassembling things and studying them in detail. So we tend to take something apart and take a look at it in its parts and to become specialists and to specialize more and more narrowly. That's valuable, and I don't want you to take anything that I'll have to say as denigrating the value of what we do as specialists, but I want to discourage us from the view that this can be mistaken for a systems understanding or systems engineering. So when we take something apart and study it, put it under the microscope and study a piece of it, we're learning something of value, but we are not in any sense learning something about the system itself, because in order to understand the system, we have to understand it as a system. For us as systems engineers, it's all about relationships, just as in biology or in physics or in the other disciplines, the characteristics of the system come from the interactions. In our systems engineering discipline, the value of the system comes from the relationships, from the interactions of the elements of the system. This is the broader schema that we use for understanding the different domains and different kinds of elements of systems as we study them in the engineering field. So we find that using this schema where requirements become the basis of behavior, and behavior is allocated to components, and components perform the behavior, and the behavior is based on the requirements, that kind of bidirectional traceability gives us the characteristics of the system, and we verify and validate that system as a solution to whatever the purposes or problems that the system solves based on those relationships and that behavior. So when we split the elements apart, we're performing the kind of destructive dissection that Capra was warning us about. We have to be very, very careful about that, because as he told us, the nature of the whole is always different from the mere sum of its parts. So if we drill into these domains and split them apart, we are performing a dissection that can cost us understanding of the system. So how do we do that? What is it that we do that tends to take our systems understanding apart? Excuse me. The first thing that we do has to do with the division of the domains. We tend to divide the work in the domains into different categories, and we focus in different ways. I come from a process background, so I have an understanding of the behavior, the functionality, and I tend to look at that and think in those terms. It becomes easy for me to get blinders on with respect to that particular area of the systems domains. Other people will tell you I'm a requirements engineer, or I work on the physical architecture, or I do test and evaluation. All of those things are fine, but we should not mistake any one of those things for systems engineering. Systems engineers are responsible for looking at the entire system, so we can't, as systems engineers, divide up the different domains. And what happens is when we look at the domains in a divided way, we find that we develop tools in each domain. So we have requirements tools, we have functional analysis tools, we have physical architecture tools, we have test and evaluation tools. And so the tools further solidify the stovepiping that goes on from domain to domain. The other thing is that they create or make worse an existing communications problem, because now in order to try to cobble together an understanding of the system and the system design, we have to get the tools to talk back and forth to each other. And so we find ourselves being pulled apart, not just by our view of the domains, but by the very existence of tools which focus on one domain or the other. Now we have another way that we kind of slice and dice the systems world. We have emerging disciplines. We have a focus on complex systems or agile systems of systems, lean systems, software systems. We have different ways of looking at systems. So we might look at software systems in two different ways. Or more than two different ways. But we tend to have these emerging sub-disciplines, and what winds up happening is that we wind up getting languages that grow up around these sub-disciplines, and so we make divisions, we fracture the world of systems, and we draw ourselves apart rather than integrating ourselves together. So one of the things about our solution here at Vitech and our mindset at Vitech is that we think that we need to have an integrated view. We think that in order to be successful, we need to be all about integrating our view. And what that means is not that, for instance, we would dismiss these emerging sub-disciplines, but we would recognize them as applications of a set of broader principles, that we would be like Capra and Heisenberg and Bohr and Einstein, and looking at how these different sub-disciplines are alike, looking at how they integrate, looking at how they relate to one another. And the way that they relate, the way that they are integrated with one another, is the way that's identified by Capra. And the way that we think about it at Vitech is that all of this is integrated through the systems view, through understanding the system, through understanding that it all turns on the relationships, and that we need to take it as a view from the system perspective in order to understand the system. So truly, we feel like we should get our insight from integration, because that's the way to insight for the systems view. Now let's talk about the other aspect of our mindset, and that is models. And of course our first question is, what is a model? Well, a model is a limited representation of a system or process. So to begin with, we know that the model is not the system itself. It's a representation of the system. It's limited, and to be successful, the limitation needs to be drawn by what's relevant. So we use all kinds of different models. If I ask everybody to take a minute and draw a picture of a horse, you would draw that picture out of a model that you have in your head of what a horse looks like. If you colored it in, some of us might color it brown, some of us might color it black, some of us might color it like a pinto. We would have different ways of representing it, all based on our models. When I was a kid, I liked to build models, and you would build a model, and the deal there was that the model needed to look like what it was a model of. So I had a model horse that I built and painted, and the key aspects of those models, the model of that horse, was that it looked like a horse. So the limitation of that representation was it was limited to looking like. Now, it didn't work like a horse. It didn't eat hay. It didn't run. It didn't do all of the things that a horse could do. So that wasn't a part. My model was satisfactory even though it didn't work like a horse because that wasn't the object of the model. But if I'd been trying to model how a horse works, then I would have had to use some sort of a representation that included that. And that's one of the tests of a good model is the limitation of your representation, does it include all of the things that we need it to include? And that speaks to the second point here, because in the systems engineering world, we're looking for a model that can be migrated into a cohesive, unambiguous representation of a system. Why? Because we're ultimately going to try to get the specifications for building a system out of this model, or we're going to use it to test the model. So this is a piece of how we define the limitations of that model. Now we have a tendency to talk about model-based systems engineering or model-based engineering. All engineering, all problem solving, as a matter of fact, is model-based. Why? Because, as I said with the example of drawing the horse, we communicate out of a model that we keep in our head. So we have a model. We can't really communicate about a problem or about a solution except by talking from the model that we're using. Now the issue becomes whether or not we're going to use a model that is surfaced so that everybody can work from the same model or not. Are we going to use different models that we keep in our heads and undergo the very difficult process of trying to get those all aligned? Are we going to work from models that we scatter around through a tool set and attempt to make sure that all of those are perfectly aligned? Or are we going to use a single model that we can put out where we can see it, where we can work with it, where we can manipulate it, and where we have a common understanding of what it's about? And this is the sense in which we at Vitech advocate as a part of our solution. We advocate that the model should be one that's surfaced, that everybody can deal with, that it's accessible to everybody, and we can all be aligned on what the model is, and should not be fragmented or spread around, either individually or spread around as different models of the system. So when we talk about the Vitech mindset, we take a systems view and we get a broad enough view to include the interrelationships and the interactions of the elements of the system, and we work with that view in a model. So that's why, as we now begin to talk about our methods and our tools, that's why we choose the methods that we choose and why we choose the tools that we choose in order to further this mindset of taking a systems view and using models to make that view come to life. So let's talk about the Vitech methods. We call our method strata, which comes from strategic layers. Basically, what we're talking about in a generic sense is layered model-based systems engineering. Remember our schema, and we'll keep track of where we are as we go here in our schema, but our methods are designed to implement our mindset. So our mindset is why we do the things that we do, and our methods are the way that we're going to do them in order to implement our mindset. So what we do is we work in layers. We try to understand a system from a very high level to begin with, and we'll talk about why that's so. And then we work with the system in developing a model and developing our understanding of the system by increasing the level of detail. We increase layers of detail as we go, and we try to do what we call increasing the granularity. In other words, as we move from layer to layer, we advance the granularity and increase the detail. We do that so that the decisions that we make about our solutions, about our system designs, can be done in an orderly fashion. And we can let our design decisions emerge as we increase the detail. The model shows us, guides us to the kinds of decisions that we need to make and the kinds of design choices that we'll be making. So we increase the detail gradually, layer to layer. Now, this doesn't mean we do 20-layer models. It would be a rare model that exceeded 3 layers of granularity. But be that as it may, there is a definite change in the level of granularity as we move layer by layer down to a more granular view. But we're doing this so that we can get completeness at every layer. In other words, we can have an understanding that works across all 4 domains at each layer, and then we increase the granularity and we develop further understanding. And we'll talk about why we go through all 4 domains at a time. So, how does this further our mindset? Well, we can think about that by looking at 2 basic principles. One is that we begin high, and I talked about a high altitude view. We do that because it supports innovation. It enables us to understand the system, the problem, and the solution in ways that support innovation. It provides us vision for making our choices, and it allows us to manage our alternatives. And then we advocate that we work in all 4 domains, layer by layer, so that we get a complete layer to any given level of granularity, which allows us to converge on our solution, allows us to operate in a very orderly way. So, the first thing is we begin high. We do that first because it supports innovation, and secondly because it gives us an appropriate level of vision, and it allows us to keep track of our alternatives. So let's talk about innovation for a minute. Innovation occurs in 3 different stages. Now, these are not bright line divisions between these stages, but it's a gradual metamorphosis across the stages. We begin with lots of ideas, which we call prototypes here. Lots of ideas about how we might solve a problem, for example, but we don't invest much time, much detail in those ideas. We are testing, we're looking, we're thinking, we're making relationships. The French mathematician Henri Poincaré said that creativity is the ability to see the relationship between things that are not alike. We did a webinar a little while back that included the example of the Gutenberg press. And we talked about Gutenberg incorporating metallurgical principles for casting type that would be movable together with an agricultural press to apply the pressure for the inking and the inking chemistry and division of labor techniques. But this was all made possible by his ability to look at dissimilar things. As you look at the world early on and you see different kinds of possible solutions, you don't invest lots of time in any individual solution, but you can be very, very creative. As you move toward ideation, you begin to narrow your possibilities down, look at solutions that are more and more likely. And finally, as you validate, you're converging on one particular solution, and you're validating that back against what you're trying to do. So beginning high allows you to get that vision, especially at the inspiration stage, and to make those kinds of decisions. Now, getting vision. This happens to be an aerial photograph of the parking lot in front of my apartment in Baltimore. And when you go out of my apartment, if you're going to go from my house out to Route 100, which is a main east-west thoroughfare, and you're going to want to go somewhere, you've got to either turn right or left on Tamer Drive. But if you're looking at the decision from this level, all you can see is I need to go right or left on Tamer Drive. There's not much rhyme or reason to it. What you have to know to decide whether to go right or left are, what are my alternatives for getting to Route 100, which here is labeled in the upper right-hand corner. It snakes around. It's called the Baltimore Outer Beltway. But you can basically see from the vision at this level that there are 3 possible routes to use to get from my apartment on Tamer Drive to Route 100. Now you have a way to make choices. When you have vision at this level, you know how you can start to make the choices that make up the decision branches that you're facing. So we need to get high enough to get a vision to be able to understand our choices. And the next thing has to do with our selection of alternatives. If we begin at the point of Q here, we have 3 ways that we can go. So we can look at a high level, a low level of detail. We can look at a high altitude view with a low level of detail and see these 3 choices. But the minute we decide that, okay, we're going to start at this level where I've put the star, we're going to go down to this level, something begins to happen to us. Because once we've decided to go down to that level, then we've already made an assumption about which choice will be made to get there. So we cut off 2 of the main paths with a number of alternatives have simply been dismissed. So when we start at too high a level of granularity or too low a level of view, we begin to cut ourselves off from intentional choices. And we don't have the alternatives open to us any longer. So we need to be taking a high-level view and making intentional choices. Making intentional choices promotes the quality of our solution. Now the next principle, once we've begun high, is that we need to work in all 4 domains. We need to work in all of the domains of classic systems engineering: requirements, behavior, architecture, physical architecture, and verification and validation. We need to not forget those. What happens is if we advance the granularity in 1 or 2 domains and forget the other domains, we create a situation where we're going to have a good deal of rework. Because when we go back and catch up the domains we've forgotten, we're going to find out that they're tied. Remember our schema. Remember our relationships. These domains are tied together. They're in relationship to one another. So if we develop 1 or 2 of these further than the others, then we're going to have to go back, and that's going to impact the relationships, and the impact on the relationships is going to have to be tracked back into the domains that have been advanced, and we're creating rework. So we need to avoid that by bringing them all forward and making our intentional design choices in all of the domains as we go. That keeps us from having broken relationships, relationships that are not being fully considered, and allows us to be intentional and increase the quality there. So when we talk about our model mindset, we talk about using the model beginning high and working in all the domains as we move through our layered model. A lot more could be said about that. We could have individual webinars on a lot of topics here. But that's the basic overview of our philosophy about models. Now let's talk about our tools. Remember, our tools leverage our methods. So we use the tools to leverage the layered model-based systems engineering. And by tools, I don't just mean software tools. And we'll talk about the supporting tools of training and services as we get into this. But let's begin with the first layer, or the first level of software tools. One way we could look at tools in terms of leveraging the methodology is we could adopt a view of the tools as just dumb storage. In other words, the tools would simply form a file cabinet in which we could store and then retrieve direct inputs to the system. So if we have a use case diagram that describes the system, we could do the use case diagram and file it away. Same could be said up here for an EFFPD or for the activity diagram that's hiding back there. We could simply do those one at a time, file them away, and retrieve them as we went. The problem is the tool can be much more helpful than that. If you put documents in a file cabinet and then you put a changed version of the document into the file cabinet's not capable of changing all the other documents to reflect the changes you made in that one. So we want our tool to be a little smarter. We want it to do more. And our conception of an effective tool is that it will capture information about the system, not just the particular input or the particular representation, but it'll actually capture the information that's there in the representation. So if you look here and you see a component diagram, you know in this case that the workstation and the command center are part of the geospatial library. So we want the tool to capture not just this representation of that, but we want it to actually capture the relationship. And then we want the tool to maintain the information that it's captured in that relationship. And if it gets more information about those relationships or the elements, we want it to be able to update it, because we want to be able to ask the tool for any kind of representation that we've told it that we might want, and get that information back in a representation without having to redo it ourselves. Pretty tall order for a tool, but it can certainly happen. So our tools, our software tools, are set up first for ease of use. You can draw diagrams, you can enter information into property sheets, you can ingest documents, you can get information about your system or your system design, changes to your system into the tool relatively easily, and the tool will capture those. And then we're going to ask the tool to format that data for retention. In other words, to hold that data that it gets and keep it for further use. So the tool maintains the data. Now this gives us an advantage because it allows us to manage complexity. So in other words, it'll remember all of the different links that are associated with a particular component. And it provides discipline. It uses a particular syntax or grammar to catalog the relationships that we have. Those are already in the tool, and the tool enforces the discipline that is embedded in its schema that creates a meta model of the system. And so as you put information about a particular system into the repository, it's managing that meta model. It helps you to manage complexity, it helps you to maintain discipline, and it does that through the meta model. And the foundation of the meta model is our familiar schema here that we talked about, with the bidirectionally traceable relationship between requirements, behavior, components, and back through from components to requirements again. It provides simulations so that we can verify. It provides consistency checkers, provides ways of being able to test the information and to look at what's in there and to develop a fully relational description of the system. Now, we also want it to return information. So we want the tool itself to be able to reformat a particular subset of the information and return it to us the way we want it. So this is really the very same information that we saw earlier in another form being taken into the system. We want the tool to be able to produce this, and we want it to do that through handling queries. Queries basically of our tool take the form of saying, give me the following information, and your request specifies a subset. Now, typically you do that not by writing a query, but by simply choosing a number of representations, because any given representation is going to be composed of a particularly defined subset of information about the system or the system's design that's presented in terms of rules. So the second part of the query to the system says, and give it to me according to these rules, which are the rules that govern the representation that's to be produced. So if you click on a tab or an icon that asks the system for an activity diagram or for a sequence diagram, it says, give me the information that's defined to be in an activity diagram and give it to me according to the rules for the production of an activity diagram. So for example, you might say, give me the functions in this process with inputs and outputs formatted as a SysML activity diagram. The tool is set up so that you can make those requests that follow the standard rules for those representations and get that out of the system. So what you have is a tool that allows you to input information in a variety of ways. And the tool takes that information, holds it in the framework of the meta model, holds it in relationship, and then allows you to query it and specify the information in the rules, and to query it very simply, not by formatting a query, although that's possible, but by pushing an icon, pushing a button, by selecting a view, sending a query to the system, and then getting your output in whatever particular format you'd like to have the output. So the tool does the output itself. You don't have to redraw it. So you don't have to say, well, let me look at the activity diagram and I can look at that and then I can redraw a sequence diagram. The tool handles that for you because it has the meta model built in. We think that's the true way to leverage our methodology and therefore to implement our mindset. So our software tools are designed to have a user-friendly capture interface, and then the interface maintains the discipline. So for instance, when you drag a component onto another component, the tool will give you a suggestion and say, this relationship gives you a choice of the possible relationships. So it actually maintains the discipline as you put the information in. and then it maintains the data structured up in the meta model and will return specified data on demand in the desired format. That's true leveraging of the methodology as you move through the layers of your design. Now, the software itself is not sufficient. We think that the most important thing that we have to offer as part of the Vitech solution is our mindset. We think that's very helpful. We think that sometimes we tend to lose sight of that. Sometimes that's not well understood. So we think that's very, very important. We think our methodology is important. Understanding how to approach problem solving using that methodology. And finally, you need to understand the tools. You need to understand the true power of the tools and how to implement them. So we offer training in all of that. We offer training about our mindset, about our methodology, and about our tools. Further, we provide mentoring in all of those areas. So as you begin to use the tools to leverage the methodology to implement the mindset, our engineers can provide mentoring as a part of our solution. In other words, we think it's important not just to abandon our customers to try to figure this out for themselves. We also offer problem-solving services. We get to encounter a wide variety of things moving from customer to customer and problem to problem, so we can offer the benefit of our experience in solving different kinds of problems. And then finally, we pride ourselves on our customer service. So we try to answer questions and help folks along and provide what they need to be successful. So what do we make of this? We've been at this for about an hour. What would I say if I had to lift some things out and leave you with some things in conclusion? The first thing is that anything that fragments the systems view robs us of the power of our discipline. This comes from our mindset that we get insight and understanding in the system through integration, not through tearing it apart. So for instance, our tagline is not insight through dissection, but insight through integration. The systems mindset promotes the ability to bring to bear disciplined thought about complex problems resulting in quality solutions. The mindset promotes that, and the methodology promotes it, and the tools promote it, because we try to take away the clerical work that's necessary to keep everything in balance. We try to give the tool the clerical work type of functions in maintaining the discipline so that we can focus, as we work in systems engineering, we can focus on the systems mindset and bring that to bear on complex problems and generate high quality solutions. We think that the layered MBSE implements the systems mindset and allows us to begin high and advance the design in layers, making intentional design decisions. The more intentional we can be about our design systems, the more we can be the engineers that we want to be and focus on what we need to do to accomplish our purposes, rather than what we need to do to maintain all the information about the system. Our tools are designed to leverage the layered approach by supporting order and discipline with a design model that's current in real time. As you put information into this model, it changes the repository, which means that if you look at the model through another window, through another view, it's changed in real time. It's important to note that documents in our world are simply a different kind of a view into the system design. So when you get ready to generate a particular set of documents, you're giving exactly the same type of query to the system. Give me this subset of information defined as what needs to be in this document, and give it to me in this format, which I've defined for you. The system itself has some definitions in it, but you can also customize those. You can say, you can even create your own documentation. But because it all operates on a query system, it remains current in real time. It reflects the state of the design at that given point, and further it goes into exactly what you want to go into and presents it exactly the way that you want it presented. So if I were to sum up, those would be the 4 things that I would have to say about this. At this point, I am more than happy to take your questions. If anybody has those, I think Katie and Bethany have been tracking them. So I'd be happy to take questions.
All right, thank you, Zane. We do have a few questions, so thank you to our participants. If you have any questions, we are still taking them, so you can join the discussion by using the questions panel in your webinar control screen. The first question is from Eric. He says, I see myself as a systems thinker, but my organization isn't interested in being intentional about the systems approach. How would you recommend that I get started in sharing this approach with my team?
I think probably one of the most effective ways is to approach it from the standpoint of decreased work and increased quality. For folks who don't want to do the systems thinking approach, they generally don't understand that by attempting to put all these balls in the air and juggle them themselves rather than looking at them systematically, they don't really recognize how much work that creates. And so thinking in a disciplined way decreases your work. The second thing that it does is that it allows you to make those decisions intentionally without trapping yourself, without going through too many gates too quickly and too unintentionally. So I think your pitch to a team that's not engaging in systems thinking is that you can increase quality and decrease work.
All right, thank you. We've got one more question from Keith. He asks, is the strata method the same as what you used to call the onion method? If it's not, how is it different?
It is indeed the same. We just put a name on it. Jim Long, who is he's David's biological dad and our intellectual dad, was the father of that method of looking at problems and solving the problems by peeling the onion. We simply gave it a name and changed it a little bit in terms of packaging, but not at all in terms of content.
All right, thank you, Zane. That does wrap up our questions and answers for today's presentation. If you have any other questions or comments for Zane, please don't hesitate to shoot him an email. You can see his email address on the screen right now. Or you can post your questions and comments in the forum of our community site at community.vitechcorp.com. I will check that out before we close the presentation. We are ready to wrap up today. Please be sure to register for our next webinar happening on April 29th. We're going to be introducing the new features and capabilities of our latest release that will be coming out, Genesis 3.0. You can register at the link that I'm also going to send out via the chat window. Also, one more note. At the conclusion of today's webinar, a survey is going to open on your screen. Please take a moment to give us some feedback on today's presentation or on what topics you'd like to see covered in future webinars. And that's it for today. I'm going to go ahead and get these links out to you guys. And I hope that you all have a wonderful day.